Right, question 2. So you can see this is about a spring that's getting extended. This is the classic Hooke's law practical. So complete the following sentence. The extension of the spring is the distance between the positions labelled and on the meter ruler. So it's A to B, that's the length of the spring. Okay, so you can see A to B over here is, that's the unstretched length of the spring. Okay, but now the spring is got a new length. Okay, so this is like length 1, and now it's got a new stretched length, which is length 2. Okay, and the extension is the difference between those two lengths, right? So it's from B to C. Okay, that difference there, that's the extension of the spring. The type of energy is elastic potential energy. Oh, pen's just stopped working. There we go. Elastic potential energy. The word potential just means stored. So elastic potential energy. Two things that the student can do to improve the accuracy of the practical and the data collected, right? So, how can we make sure that the results that we're getting are accurate? Well, one thing that you could do is when you're taking the results, you could get down, you could, bend your knees so that you're at eye level, okay, so that you can easily measure, actually that's not what we're looking for, is it? Sorry, you're measuring from that point on the spring there. So we need a way of making sure that we're kind of measuring horizontally across to the ruler, and one way to do that is to bend down and get to eye level. All right. Another way that you could do it is to use something called a fiducial marker. Fiducial marker, which is basically like a little arrow that points over to the side there, right? So that you don't get parallax error when you're doing that. Now you can see that this is a meter ruler. Okay, but obviously it doesn't measure in meters, does it? Most meter rulers, would measure in millimeters. But you could go for a ruler with a finer scale or with a smaller scale on there. So you've got to be careful how you say that. Okay, if you said use a centimeter ruler, then that wouldn't make sense, because you'd end up with a ruler that was 1 centimeter long, which wouldn't be any good for anything, right? Okay. If you said, use a ruler with a finer scale or a smaller scale or a more precise scale, okay, then that would allow you to get the mark there. And then the final thing that you could do is you could, do each reading 3 times, okay, and take an average, and that would, of course, allow you to discard any anomalies as well, right? So the idea of repeating the experiment, for the same force, so for each time you measuring the force, then you're going to take the reading 3 times or 5 times, take an average, and then that allows you to discard any anomalies. So the graph shows that the students made an error throughout the investigation, okay, and actually the graph for a spring should look like this, shouldn't it? It should look like a straight line through the origin, which then curves up when you go past the elastic limit. Okay, so that's the problem right there. So how is it that their whole graph has been shifted up by 50 millimeters? Okay, and it's because they've measured the length of the spring, not the extension. They've plotted the length of the spring, right? So the length of the spring here is 50 millimeters. Okay, and you can see that because it doesn't go through 0, 0. All right. And now we need to mark on the limit of proportionality. Okay, well, if a line is proportional, it's when it's a straight line through the origin. Okay, and you can see that it stops being a straight line, not up here, it stops being a straight line after this point here. You can see it's already starting to curve, okay, at that point there. So this point is well beyond the limit of proportionality. Like if we were to draw on the graph where the limit of proportionality is, then we would put it there, Okay, everything on this side of the graph is elastic behavior. Okay, because the spring will return to its original length, and once we go past the elastic limit, then we get into the plastic region of the graph. Yeah, so our reason for choosing that point is because the line curves at that point. Second spring, same initial length, but which is stiffer. Okay, so stiffer is used, and this spring does not reach its elastic limit. So we want to plot a graph of extension, okay, against force between 0 and 8 newtons, right? So the first thing, if we're plotting extension, okay, then we have to draw a line that goes through 0, 0, all right? And then this one is stiffer. So that means that if we put the same force on, we're going to get less extension. So your line has got to have a lower gradient than the initial graph, right? Because it's a stiffer spring. So again, look, you can see for the same amount of force, okay, this one has got that much extension, this one has got that much extension, so less extension for the same force. And all of the graph, it doesn't really reach its elastic limit, so all of the graph is straight. There's no curved section of the graph. And that's the end of question 2.